demonstration. Welcome to the Theoretical Chemical and Computational Modeling workshop. We started with the first speaker, Rin Chiari. Okay, so he will speak about predictive modeling of the activation energy of petroleum sludge pyrolysis using artificial intelligence approaches. Okay. Yes, yes. Okay, and the first, that is the first slide? No. Ok. Se mette seduto lui, mi sa, le lasci. Ok, so please. Okay.
Thank you. Good morning, everyone. My name is Karim Khiari. I'm a chair researcher in the Polytechnical School of Algiers in Algeria. I will talk today about predictive modeling of the activation energy of petroleum sludge pyrolysis using artificial intelligence approaches. Here is the plan of this talk. I will start with the introduction, the problem statement, and the industrial and environmental context of petroleum sludge. Then, the general overview of pyrolysis and the concept of activation energy. The core of the talk is the experimental part, where I detail the methodology of compare three AI-based modeling approaches such as ANN, RDF, and a hybrid model such as RDF-GA. I will finish with the conclusion and the perspective of the work. The rapid growth of the world's population combined with rising productivity and consumption generate increasing worrying amounts of waste, which puts strong pressure on economies. Fossil fuel-based energy production is one of the main contributors to this environmental degradation. In Algeria specifically, drilling production and refining operates generates a large volume of industrial waste, among which petroleum sludge is particularly hazardous. It's composed of heavy metals, polycyclic aromatic hydrocarbons, sulfur and nitrogen compounds worldwide, and estimated about 16 to 18 million tons of petroleum sludge are produced yearly. Petroleum sludge is generated at a different stage of oil and gas production chain, mainly during refining operation and in storage tanks. Disposal mainly relays and incineration, solidification, chemical oxidation, or biodegradation, but only a small fraction is actually recycled or transformed into useful products. Inadequate elimination causes groundwater to pollution by leaching and ambient air to toxic emission through valorization. Treatment technologies for petroleum sludge must therefore satisfy a compromise between two dimensions. On one hand, compliance with strict environmental regulations limits. pollution. On the other hand, the reduction of treatment cost and the economic value that can be recovered from the sludge through energy or material valorization. This dual content is exactly what motivates the research for an efficient and profitable valorization route, which brings us to pyrolysis. Following this, the aim of our work suggests is to produce a diesel-like fuel from petroleum sludge using the pyrolysis process, to characterize the fuel produced according to international standards, to determine the activation energy, key of this work experimentally from TGA data, and to predict the activation energy with 3 models such as INN, RBF, and the hybrid model RBF-GA. Similar treatment and valorization method exist for petroleum sludge, such as solvent extraction, centrifugation, microwave heating, ultrasonic wave. In this work, we will enter to the valorization by pyrolysis. What is pyrolysis? Is the chemical decomposition of an organic compound by the significant increase in its temperature to obtain other products. We have at the end of the reaction 3 phases such as liquid, solid, and gas. The study of pyrolysis mechanism requires the determination of the key parameter govern the reaction rates, such as the activation energy, which is the minimum energy required to initiate chemical reaction, and to determine the reaction rate, the higher the energy activation. And the energy activation depends on the nature of the reactants and the experimental conditions. We can estimate this energy of activation on applying the conventional model, such as Friedman method, Ozawa, and Kissinger method. The activation energy was determined from TGA, which show the mass loss of petroleum sludge as a function of temperature by following the composition rates for a different heating rates. The adopted methodology is shown in the slide. The petroleum sludge was collected and underwent pre-treatment operation by centrifugation. The pre-treatment oil served as the sample for oil batch pyrolysis reaction. The pyrolysis oil was characterized according to the standard conventional diesel method. The experiment was carried out with a load of about 200 grams of matter and the heated rate of 12 degrees per minute and a nitrogen flow rate of less than 2 milliliters per minute. No condensation was observed before temperature of 372 degrees. The condensation of pyrolysis gas then increases with temperature, reaches a maximum at 430 degrees, and then decreases toward 475 degrees, indicating the end of the reaction. To check the quality of the liquid phase is our produced fuel. We characterize the fuel, and we can observe that the most of the physical chemical properties are good. This work aims to demonstrate the effective of hybrid approaches based on artificial intelligence in the reliable prediction of kinetic parameters, thus opening new perspective for a better understanding and optimization of thermochemical valorization processes of petroleum sludge. Before modeling, we need to define the high-dimensional input space, three families of input variability of AI meta model, such as the approximate analysis, elemental analysis, and biochemical composition. And as a response is obviously activation energy. Our first attempt was a standard artificial neutral network, ANN, as you can see on this scatter plot of predicted versus experimental activation energy. The points deviate significantly from the ideal y equal x line. The coefficient of determination is only about 0.26, conforming to weak correlation. Facing the weak performance of the ANN, model, we test a radial basic function, RBF, known for its robustness against noisy data. The coefficient of determination improved to 0.5, a noticeable gain translating into better agreement with the data. The RBF network uses a Gaussian function. To overcome the previous observed limitation, a hybrid model combining the RBF with genetic algorithm was developed. This advanced approach allowed for the dynamic optimization of the model's internal parameters, including center weights and weights, leading to the significant enhancement in predictive accuracy. The coefficient of determination in this third model is about 0.79. Here we present the comparison between activation energy predicted by RBF GA, the hybrid model, and experimental values obtained from iso-conversional method across the whole conversion range. Both pure follow similar trend. The activation energy arrays fixed around the conversion ratio of 0.50. The model correctly identified this critical reactivity point. However, we do observe a symmetric underestimation across the whole range. For example, for alpha equal 0.8. To summarize, among the three models tested, the hybrid RBF model clearly outperforms the standalone ANN and RBF models, reaching an coefficient of determination of the 0.79. And we can say that the computational tool for optimizing reactor design and operating parameters, enabling efficient large-scale visualization for petroleum sludge in line with sustainable energy recovery goals. As perspective, it's can say that validate the model on a wider experimental data set and extend the approach to other waste streams such as biomass or sewage sludge. And thank you for your attention. I'm here to respond to your questions.
Okay, thank you for this talk. Now the paper is open for some questions, some discussion, some curiosity.
The correlation coefficients you have shown, So normally in this kind of studies, this is a good result. I mean, 0.79, which values normally you are okay. So I mean,
it's okay or not okay?
No,
I don't understand.
It's not okay, but I don't know. Because
So
I don't know which values are good for a correlation.
The correlation, the good one is this one.
Yeah.
If coefficient of determination in the perfect case is about 1.
No, I know that.
Okay.
But, so the deviation from the optimal value, which is 1, of course, is not large in this case. No.
Yes.
In this kind of study, so it's acceptable. It's 0.0.
Yes, I think if we compare the three model.
Yeah, of course.
Yeah.
First one is not correlation.
Yes.
Correlation.
Yes.
Because normally it's near to 1.
Yes.
This is the idea.
Yes. Here only far, but here only close.
Yeah.
Is the best. The hybrid model is the best. And between the three model tests.
And any idea to improve it even more? So to
we will to improve it. We will test the other model. First one, the first way. The second way is to use a large number of data. Here we are used about 500. Yes. In the future work, we will focus to use large model.
Okay. Thank you.
Thank you. Thank you. Okay. Abbiamo persone che vogliono connected. So now the next speaker is a virtual speaker. I don't know if he is connected. No sé. No, because como es un no funciona. Porque no ves. Entonces tenemos que tener con dedo. No sé si tiene el mouse allí, está incorporado. porque este no. Okay.
When the presenter is ready to share.
Yes, okay. So the next speaker is Luca Mancini, and he will speak about theoretical investigations of CO2 into molecules separate in the gamma graphene membranes using a classical molecular simulations study. Hello, Luca.
Hello, good morning. Can you hear me? Can you hear me?
Can you hear us? Can you try your microphone? Because we can't hear you.
Yes, I can hear you. And I can also see that my microphone is working, so. Can you hear me now?
Mancini, we can't hear you. Maybe you can try a different browser. I suggest you to use Firefox or Google Chrome, or to check the settings of your microphone in your laptop, because we can't hear you. No, we can't hear you.
I'm trying to modify them. Now? Now it's okay?
Now she left the meeting, maybe to try and reconnect with a different browser. I guess that he could hear us.
Luca, non ti sentiamo. Se hai Firefox come browser.
C'ho Chrome, come diceva lui. Però qui
No, lui...
il microfono funziona.
Aspetta un secondo.
We still can't hear you.
He is using Chrome.
Okay, he's using Chrome. Okay, maybe he could check the settings of his microphone and in the user interface of
He heard you. He heard you.
You can hear me? Okay. So in the user interface, the first icon on the left, the microphone, please check your settings and test the microphone.
A lui le da che funziona su differenti browser perché vede le astine che si muovono quando parla. Poi che prova a entrare e uscire.
Yeah, maybe, yes.
Luca, scollegati e ricollegati.
Ok.
Ora adesso.
No, this is what our speaker, they are working. So I was also checking our speakers.
Okay, the test is works.
Yes, this works.
Okay. Okay. Wait, and that's a
Try and reconnect maybe now.
Okay.
Sentite adesso?
Yes,
Sì.
okay.
Okay,
Perfectly.
just a moment because it's not a share with here.
Ok.
Just a moment. Project. Okay. Okay.
Okay, now you
Okay, Luca, try to share the slides.
Ok. Vedete?
And not yet.
the moment we see you, but we can't see your presentation.
Ok.
Maybe try to share all window or all desktop. You cannot see the button to share.
Sì, sto and in principle it's shared. I don't know why it's not working.
No, so you share. We can see you, but not the slide. Start screen sharing. Queste mouse are you?
No, it's mine.
Ah,
You should share the entire screen.
Ok.
alla prossima cosa seguente. Ma c'è per fare la prova, c'è la possibilità per fare una prova al meeting. Luca, what is the problem?
I don't know. I'm sharing. I'm on the sharing button, and I'm choosing full screen.
Okay, okay, so maybe I try and share and I show you the procedure.
Okay, I think I'm doing that.
Or in the worst case, send us the presentation and we move the slides.
Okay, now I am sharing the screen. So you go on the sharing icon.
Yeah.
And,
Yeah.
yeah. Okay, so I try and guide you because it doesn't allow me. So you see menu, select window or screen, you select entire screen. Then you go and click on the screen.
Yeah.
Okay, on the preview of the screen, you click on the preview of the screen, and then you should start sharing the screen. Then you move to the presentation and set it in presentation mode, and you should see. Before it was working. Before we had an issue with the microphone, but the presentation was working.
Yeah, because it was the other browser. Now I'm using Firefox.
Okay, but it should be the same thing. Because
Yeah,
if
yeah.
you-
Just a moment. It's loading. I don't know if you see something.
No, we still don't see the presentation. We can see you, but not the presentation.
Okay.
Okay, so maybe we move.
Luca,
See?
we move to the next speaker, and we try it later. And if we are not able, we just send us or me the presentation, and I check it here. Okay.
Okay, thank you.
Okay. Prepare to send the presentation me. Okay. So sorry, the technology is very hard, and so we move to the next presentation is by Piotr Dudza. I don't know if I pronounce find the surname Dudza, and he will speak about from bioemu monomer ensembles to amber reading hollow models, subunit aware quality control of a cofactor rich aldehyde OC reductase. Okay, please, thank you. Ok? È pronto? Puoi iniziare?
Yeah, one more, please.
Ah, ok. Okay.
Good morning, everybody. My name is Piotr Lipa, and I would like to present to you today our work that we did with Professor Marek Wojciński as well as Professor Maciej Szaleniec on predicting protein conformations. As you may know or may not know, proteins are not static structures. They tend to adopt different conformations. And BioM was developed to predict those conformations quickly and efficiently. However, this is not simply enough for oxidoreductases, which are cofactor rich. So we therefore asked whether biohomogenerated structures can be used later on in the molecular dynamics.
I have to interrupt you. Yes, sharing the data is going on the presentation. So yes, please.
Mhm.
Now, so we, like I said, we asked whether BioM can generate structures that can be later used for follow control in the BioM molecular simulations. The motivation behind our work is very practical. Currently, most molecular dynamic simulations begin from one experimental backbone. This is well grounded. However, essentially, not every single simulation starts from the same backbone, which can be very time-consuming and costly for new discoveries. BioEMU aims to solve this problem by presenting different alternative conformations before we invest in lengthy, timely, and cost-consuming atomistic simulations. We do not, however, treat BioEMU as a replacement for MD, nor do we accept all of its conformations it proposes as correct structures. Its main advantage lies in the diversity it provides before proper MD simulation can occur. However, the main difficulty here is the chemistry. For this enzyme and any other cofactor enzyme for that matter, a backbone is only useful if restored cofactors and metal centers can remain physically reasonable after the preparation before any MD takes place. So the real question here becomes not whether BioEMU can just provide different structures. It becomes whether those structures can be processed and prepared into complete hollow models that can be later modeled in molecular simulation dynamics. So the chosen system is a quite demanding one. We've decided to look at the aldehyde oxidoreductase from Aromatoleum aromaticum, which is visible here at the bottom right corner. We extracted each of the subunits from this structure. It contains the so-called AOR-A, AOR-B, and AOR-C subunits, with the AOR-A subunit localized in the center of this enzyme and being responsible for electron transfer with iron-sulfur clusters, which are also available here in those cuban-like boxes with ligating cysteines in the blue color of cyan. The AOR-B is the catalytic tungsten group, and its two subunits are placed to the sides of the enzyme, and it contains the tungsten bis metal center together with magnesium, as well as one proximal iron-sulfur cluster. And AOR-C was the simpler of the three, being the flavin-containing subunit, and it's being located at the bottom of this enzyme. So this heterogeneity is the main reason why we do not expect user reconstruction procedure, just one, or a quality control that is sufficient would need to be specific to each of the subunits. And although each of those quality controls and reconstruction procedures have to be specific, the overall path was shared for each of those subunits. We started by requesting 100 samples from BioEMU, of which 96 and 91 and 100 respectively were delivered for AOR-A, B, and C subunits, which then entered our pipeline. That required them to be aligned back to the reference. The 8C0Z is the code for this enzyme, and each of the subunits had to be aligned to the cryo-M reference in order for those cofactors to be transferred and reconstructed back into the atomic models from BioEMU. After this transfer, we also reconstructed side chains, which were not present in BioEMU conformations as a design choice by BioEMU. And then we also did solvation as well as ion neutralization in order to progress to the minimization stage. And only after the minimization have we looked at quality control of all of these subunits, as well as their placement with PCA and HDB span that I will discuss shortly. So as you can see, the logic was shared, but critically, chemical steps remained strongly subunit dependent. which one of those steps is visible here. Like I mentioned, all of them require different forms of reconstruction. The ARA required 4 iron sulfur clusters to be reconstructed into the protein. AURB required 1 of those proximal protein iron sulfur clusters. However, it also required the rebuilding of the tungsten cofactor center. And AORC, being the flavoprotein, it only required the restoration of non-covalently bound FAD, so there were no covalent bonds here, it just would be transferred to the aligned, let's say, subunit. The important part is that minimization was not the same for, or like rather, the start of minimization was not the same for all subunits. However, the later stages were identical from 1 to 6. It was a staged minimization with slowly decreasing frozen layers. The min 0 was added specifically for iron sulfur clusters. This is because of the covalent bonded nature of them with the ligating cysteines that had to be transferred from the reference backbone to the backbone of the BioM cofactor, BioM conformation. This caused local strain on those bonds, and they had to be relaxed before any other minimization could take place. Otherwise, they would unrealistically pull on this protein and cause problems down the line. Now, the second step that was chemically dependent or subunit dependent was the type of local descriptors that were chosen, as well as the acceptance rate. So for global descriptors, we decided to go with C alpha RMSD values, as well as radius of gyration to test compactness and potential energy per atom. Any energy outliers or extreme outliers in energy and RMSD values were detected with median absolute deviation criterion. Whereas locally, it was, like I said, subunit dependent. We went with the PES, or the iron sulfur cluster distances for AORB and AORA. The AORAB had also the tungsten sulfur distance as a reference. And AORC, we measured the FAD pose RMSD of the cofactor. The important part is that a low RMSD was not an essential requirement. A structure could remain globally different from cryo-OM reference structure, but still be retained if chemistry and energies were in a plausible location. So a structure in the end was kept only if no QC flags were present. And with that in mind, we can now look at the results, where we can see that most of the structures have survived the reconstruction and minimization process. Analyzing the failure modes can indicate why different subunits failed. For example, in AORA, we can see that the most common failure point was an energy combined with local geometry of the iron sulfur cluster distances. It's possible because of the amount of the highly dense protein with 4 iron sulfur clusters. For AORB, we saw that mostly energy dependent failures were present, as well as some energy and local geometry with the iron sulfur cluster. And for AORC, mostly rejections were happening because of energy and some because of RMSD and energy. So clearly, retention is the only part, is only a part of the result, which tells us that many structures have survived. However, it does not tell us whether the process or the minimization erased any of the differentiations that we have received from BioM, which is why we also did C alpha and RMSD on the backbone chain in regards to the references. So for AORA, we have remained a very displaced from the reference backbone, while AORB and AORC remained much closer. It's crucial to point out that the reference from the cryo-OM also received the exact same pipeline, and the exact same minimization stages as the BioM conformations. And the difference, or the RMSD for the reference, was negligible, as indicated by the red line, meaning that this process did not introduce much shift in terms of the global backbone, which leads us to conclude that BioM conformations were truly as a result of BioM predictions and not due to the pipeline or minimization presented here. However, being different does not mean that we are energetically stable or not strained, which is also why we looked at energy, potential energies per atom, which, as you can see, varied by subunit, and with references also indicated in a red dashed line. And most of them fell in favorable ranges, with most notably ARA actually finding more energetically stable protein conformations than the cryo-M reference. This could be because we did the only subunit and not a full monomer, which I will have full assembly of IOR, which I will discuss later. But this could be one of the reasons, or we simply found better states for this protein than the cryo-M reference. Energy was a useful sanity check here. However, acceptable global energies do not guarantee a local metal or cofactor geometry, which is also why we did another test with those specific distances that I mentioned before. The iron-sulfur distances were applied for IORA and IORB. Here I present the tungsten-sulfur distances for IORB. However, the ranges for the iron-sulfur clusters were 2.05 angstrom to 2.45 angstrom, and all of those lie within this range. So they all the retained structures are well within this range. And for AORB, the tungsten-sulfur clusters were in the ranges of 2.25 and 2.65 angstrom, which also these lie within. And those ranges were determined by MD simulations on the true reference AOR assembly. They were tested, the normal length during simulations, and that was taken as a backbone to decide whether a structure was realistic or not. Once we knew which structures were acceptable, we then asked how this diversity was organized, and for that we used C alpha coordinates on the principal component space, which we later analyzed with HDB scan method. The advantage of HDB scan is mostly that it does not force every single point or every single structure into a dense region, which would explain why many of them are marked as noise. It's important to note that noise here does not mean that the structure is chemically invalid. It simply means that it was not part of a dense enough cluster under the selected parameters. With AORA showing the clearest clustering with the highest density-based score, as well as the lowest noise ratio, and AORB being the most diffuse conformations from BioM, and also having the highest noise because of that. The results had a direct impact on the representative selection that was chosen for MD. And in the end, we have decided on cluster medoids as a good representation. Each of the clusters received one medoid representative that was central, the least distance to each other representative from that cluster. And they are represented in their respective colors, with blue representing the control structure reference from the cryo-M, and white or gray representing the noise cluster representative, that also was the least distance to all the other conformations. The selected conformations here were propagated for 51 nanoseconds in explicit solvent MD, where we did not observe evident cofactor disruption or structural collapse of the local geometry or cofactors. These runs show that selected models can be carried through MD However, it's important to note that they represented a practical stability checks, and thus alone cannot be taken as evidence that the retained set is an equilibrium ensemble, which is crucial for the later conclusion. So what was established here in our work? Firstly, that bioemu monomers can survive chemically explicit color reconstruction, solvation, and minimization. Secondly, the failure modes were highly dependent and specific to each of the subunits decided here, with AOR-C being the most straightforward one, AOR-A requiring the highest reconstruction of the iron sulfur clusters, and AOR-B being the most chemically complex one to reconstruct. Lastly, we also show that global and local chemistry indicators provide complementary information, and neither of them are sufficient enough alone to determine acceptable and unacceptable conformations. Several questions remain open, however. We studied isolated subunits rather than the full AOR assembly, like I said, which is partly due to the limitations of bioemu generative models, which generates only a monomeric structures, or at least one class. The clustering is descriptive and does not provide equilibrium populations or transformation kinetics. That would have to be done with longer and other simulations in the future to analyze the catalytic or redox behavior of those centers. So in the end, there are three main points that I would like everyone to remember from this presentation. Firstly, that bioemu can in fact produce useful backbone diversity, which can survive after reconstruction, but is not automatically ready for molecular dynamics, especially in cofactor-rich systems. Second, cofactor enzymes, like I said, require color reconstruction and very precise quality control metrics, both global and local, before any molecular dynamics can take place. Third, the retained models require further validation, and the next steps would be repeated longer MD simulations of selected structures and modeling the full AOR ensemble. So this concludes my presentation for today. Thank you for listening. I'll be happy to take any questions.
Thank you. Now the paper is open to the discussion, some curiosities and questions.
Yeah, you provide there several, let's say, several samples for each problem that you are using.
Yes.
So, how to say that? What time scale we are talking about? If you wanted to go from one to each other. That what I wanted to mean is what I wanted to know or look is considering that your method works. That if we wanted to do that with molecular dynamics, but how long would it take? We are talking about microseconds, milliseconds, or
So it depends what we are trying to see, but certain things that would be looked for in molecular dynamics, like cofactor interaction with the environment, could take micro or even milliseconds to appear. And those analyses are done on nanosecond scales or even femtosecond scales, meaning that they often take very long time to progress. And those structures that we have done here, they essentially provide a different starting point, which means that a structure can achieve, it's not yet verified, but it can achieve what we want faster, rather than waiting for long time generations. I don't know if that answers your question, but
more or less. Yes, I can see your method that is a way of save a lot of time.
Yes. So we wanted to utilize a very efficient generative model, which is the bioemu, which was made for this, and we wanted to evaluate whether actually it can produce different structures that then can shorten the time. We've also added additional structures to this beyond this recent presented here. And we've seen that with another oxidoreductase, there was a clear, because it does not predict cofactors, only the backbone chain without the side chains, without the cofactors.
Yeah.
For another oxidoreductase, we have seen an open-like state, which could be representative of a lack of cofactor and the, let's say, protein waiting for the cofactor to enter its resting place and then close, which was also what we saw in the MD simulations, that after we restored the cofactor, the enzyme started to close up. However, this would require even more crucial analysis in order to support our conclusion that yes, it actually does have a place in molecular dynamics.
Okay, thank you.
Okay, some more curiosity, questions? Thank you again.
Thank you very
to
much.
the speakers. So now we try it again with Luca, if he is able to connect, and otherwise I have the presentation.
Okay, so can you hear me? Yes.
Yes.
Okay. I'm trying to share the screen.
Just a moment, Luca, because here we see the last presentation.
Okay. Can I share? Can you hear me?
Yes,
Share
we can
button,
hear
not
you.
share,
We can't see the presentation though.
but we cannot see.
No, we can't.
No, Luca, nothing.
Okay, now we can see the presentation.
Okay.
Okay.
Just a moment, Luca, because we cannot see. Okay, we see.
Okay. So you should see full screen now.
Yes. Please,
Okay.
Luca. So again, Luca Mancini will speak about theoretical investigations of the CO2 and 2 separation of the gamma graphene membranes using classical molecular dynamics. Please, Luca.
Okay, thank you, and thank you also for the support. I know I'm a bit late, so I'll try to go faster. The project I'm presenting today is about the theoretical analysis of the interaction of small atmospheric molecules with graphene membranes. And it's actually part of a bigger project led by the University of Perugia, whose aim is to design a new generation of nanomaterials with a wide range of applications, going from medicine, hydrogen storage, the field of energy, and also carbon neutrality techniques, which is the focus of the presentation of today. And the idea behind the computational study is to start with the modeling of a small system which can be accurately reproduced with theoretical chemistry tools, and then expand our analysis to bulk simulations which resemble the real system we are working on. As all of you know, when we talk about climate change, global warming, the main actor in this complex scenario is atmospheric carbon dioxide, whose levels in the atmosphere are constantly decreasing in the last years, mainly due to human living processes such as fossil fuel combustion, industrial processes, but also factories, the intensive use of lands, and so on. So the idea is to develop new materials which are able to have a nice selective properties toward carbon dioxide, which can be used in post-combustion processes and post-combustion environments. And then one of the main materials which can be used are carbon-based nanomaterials, since their morphology presents pore whose dimension is comparable with the size of small atmospheric molecules. So they can be used to trap and remove these species from the atmosphere. The theoretical approach we are using is a multi-scale approach, which starts from with ab initio calculations on small portions of the system, which allow us to accurately reproduce and accurately obtain the parameters which are necessary to the development of the force field, which is the most important part of our work, since it contains and it should mimic all the possible interaction which takes place into the, the real environment, chemical and physical environments. And then the force field is used to perform classical molecular dynamic simulations to understand how the system evolves over time and to derive all the properties that we need, in this case, in terms of absorption, selectivity, and permeation processes. So, as we said, the most important part is the correct development of an accurate force field. And in this respect, in our group, a new formulation of the interatomic potential has been developed, which is the so-called improved Lennard-Jones, that, as the word suggests, can be seen as an improvement of the classical Lennard-Jones formulation. But in this case, we are able to have a better representation of both the long-range attraction and short-range repulsion. The formulation is reported in the slide, and as you can see, there are two main parts which somehow resemble classical Lennard-Jones, the attractive and the repulsive contribution, but we have a higher number of parameters inside the formulation. And what the driving force of the potential is that these parameters are directly linked to physical and chemical properties of the system. So we are in this way able to have a better analysis and a better representation of the chemical environments in which the process takes place. The potential is pairwise additive. It's been developed for small and simple systems such as Nobel gas dimers. Has been recently benchmarked considering a more accurate analysis such as the coupled cluster approach, and we are now moving to more complex systems, in particular using carbon-based nanomaterials. Among this family, we are interested now in graphines, and in particular in gamma graphines, whose monomeric units is reported here in the slide, in which a benzene ring is connected by a series of acetylenic units. And this leads to a particular morphologies in which we have triangular shaped pores whose dimension can be adjusted, and so it can be increased or decreased by adding or removing acetylenic units in the structure. So we move from graphene to graphdiene, graph-triene, and so on by simply increasing the number of acetylenic units in the chain. In this work, we are focusing on graph tetraene, so we have 4 acetylenic linkages in each chain connecting the benzene rings, since it's been recently synthesized in 2020. And also different stacking modes have been analyzed. So we started from this work and we decided to analyze, from a theoretical point of view, the absorption properties. First of all, we performed the DFT analysis on the monomeric unit to understand the diameter and the accessible pore, the accessible dimension of the structure material with respect to small atmospheric molecules, and we compared the data from graph-triene, and graph-tetraene, which is the target of this work. And we could, from DFT calculation with ReLIP 631G analysis, calculate the accessible pore, which is the pore which is effectively accessible to the carbon dioxide molecules when they cross the structure. And it's estimated considering the van der Waals radio of carbon of around 1.7 angstrom. And here are the results. We go from 2.8 angstrom on graph-diene, 3.7 on graph-triene, and 5 angstrom on graph-tetrine, which can, in principle, be quite big, especially for selective processes. But we still decided to continue this analysis since graph-tetrine is a material which is synthesized. So we performed our molecular dynamic analysis considering the DL Poly software, and we use this software since it's an open software and it allowed us to directly implement the improved Lennard-Jones functional inside the code. We performed NBT calculation considering an equimolar mixture of 50 CO2 molecules and 50 N2 molecules in a preliminary study at a temperature of 300 Kelvin and a pressure calculated considering the Penn-Robinson equation state of 5.2 atmospheres. The total potential has been decomposed considering an electrostatic contribution and a non-electrostatic contribution. So for what concerns the electrostatic part, we choose a point charge distribution for both N2 and CO2. We consider a mixture of CO2 in molecular nitrogen since it's the most common, the most abundant molecule in the atmosphere. So we have a 3 charge model for N2 and a 5 charge model for CO2, since it allows a better representation of the quadrupole moment of the molecule, which is one of the most important interaction between the quadrupole moment and the Lewis-Later of the graphene layers, which drives all the absorption processes. For what concerns the non-electrostatic contribution, we consider the improved Lennard-Jones formulation and a series of pairwise additive contribution, considering both the interaction between the atoms of CO2 and N2 with the carbon atom of the graphene layer, but also the interaction between the molecules themselves, so CO2 with CO2, N2 with N2, and CO2 with N2. We started with the preliminary analysis of an equimolar mixture of 50 CO2 and 50 N2 molecules, and these are some results that we obtained, including a snapshot of the final configuration of the system on the left of the slide, where you can see that the graphene layer is placed at the center of the simulation box, and the gas mixture is distributed among all the volume accessible to the system. On the right side of the slides, you can see the radial distribution function evaluated for CO2 and N2 interacting with the carbon atom of the G4 layer, and we can see that we have a peak for each interaction at around 4.5 angstrom, but the intensity of the peak is higher for CO2 with respect to N2, and this suggests a stronger interaction of carbon dioxide with the graphene layer with respect to N2. This behavior is validated also considering the analysis of the density profile of both the molecules with interacting with the graphene layer, which is indicated as the orange line at the center of the simulation box. As we can see, we have for both cases 2 peaks around in correspondence of the G4 layer, which indicates an accumulation of the molecules toward the surface of the layer, but also in this case, the intensity of the peak for CO2 are higher with respect to the one of N2, indicating once again a preferential interaction of carbon dioxide with the surface. To be more quantitative, we calculated we tried to calculate the selectivity of the absorption process. We quantified the number of absorbed molecules considering the integral on the zeta density profile for both CO2 and N2, and then we considered the ratio between these 2 values, which leads to a selectivity value of around 1.6, which indicates a preferential absorption of carbon dioxide over molecular nitrogen, but still a moderate selectivity. And this can be driven by the fact, can be due to the fact that the accessible pore diameter is quite big. So we don't have an important selective process. That's why we decided to move toward the new configuration of the system, which is the bilayer stacking, because we want to understand if the interlayer region can act as a specific site for the absorption. So we started again by the work of 2020, in which a synergistic approach between experimental analysis and theoretical prediction allowed to identify 5 possible stacking modes of the bilayer. Starting from the AA mode, which is the case in which the 2 layers are parallel one to each other, and then they are shifted of a certain angle with respect to the other. And the same work identified the so-called 9-fold stacking mode, the AB stacking, as the most stable structure. So in principle, we decided to investigate the interaction between the 2 layers with our improved Reynolds formulation, and we started from the AB stacking reported as the most stable structure, and we ran our simulation identifying a new stable structure, which is lower in energy, which is in between, which is a mix, let's say, between the AB stacking and the perfectly parallel AA stacking configuration. These results have been validated also by a more accurate analysis performed in collaboration with Professor Giacomo Giorgi at the Department of Civil and Environmental Engineering, in which an analysis performed with the CSA code allowed to validate our results and to identify this new structure as more stable with respect to all the other reported previously. So we use this configuration with the same approach of before, so an equimolar mixture of CO2 and N2, and in this case here I report the results obtained for both the radial distribution function and the zeta density profile. We can see that the trend of the radial distribution function is more or less the same as the one saw before, but in this case the intensity of the interaction of CO2 with the layer is much more higher with respect to the one of molecular nitrogen. And from the zeta density profile, we can see that the interlayer region is a particular site in which the molecules are accumulated. And also in this case, looking at the intensity, we can see a propensity toward the absorption of CO2 with respect to N2. So once again, we quantified the absorption selectivity, and we obtain a value of around 2.1, which is higher than the one before, which means that the number of absorbed CO2 is almost double with respect to the one of N2, and this is goes through the direction that we want. So the possible use of these materials for selective absorption of CO2. So in conclusion, we can say that the graph tetraene is a promising carbon-based structure for CO2 over N2 separation. The case of the monolayer showed an affinity for CO2 but limited selectivity, while when we move to the bilayer case, we have an enhanced absorption selectivity of CO2 over N2. Selectivity which is governed mainly by the interaction between the quadruple moment of the CO2 molecules and the pi system, the localized pi system of the G4 structure. So we can think about to use this structure as basis to develop new membranes for selective CO2 capture in the post-combustion processes. So this was my last slide. I'd like to thank the committee, all the members of my research group, and all of you for your attention. I think you're muted. I can't hear you.
Sorry, Luca. So thank you for the nice presentations. Time for a small curiosity question.
For questions, we have to be there. Microphone, I mean.
Yeah.
Do you
I
hear
don't
me,
know.
Luca?
Yes, quite far.
Okay. And your presentation, you didn't mention. You mentioned what you mentioned that you performed the calculations, the FT calculations with B3D functional.
Yes.
Right. Just to obtain the geometries, geometrical parameters of the molecules, or just to parameterize the improved Lagrange potential.
So we The bit-relief calculations we performed were only to compare the accessible diameter of the structures. The improved energon parameters have been already tested also in several cases before with similar work on Graph3, in which we compared the improved energons also with DFT calculation, but in that case were bit-relief with the triple zero basis set, because they contain NP2 correction, which is already used as benchmark in the past also for the interaction of CO2 with other species.
Yeah, the functional didn't include any dispersion correction, no?
In this case, no. In the previous case, yes. It was the D3 dispersion.
So it's not important in this case to include it.
Not so much, also because we saw in the case of the siesta analysis, the same analysis was performed with and without the dispersion, and the trend is more or less the same.
Yeah, of course. Yeah, in this case, because it's very dispersive, the interaction between layers, probably. Yeah. Okay, thank you, Luca.
Thank you.
Okay, thank you, Luca. So we need to move to the next speaker. Okay, the next speaker is Marcos Mandado. And he will speak about the unaffired energy decomposition of the localization approach to rare gas simmer bonding. Ah. 15 minutos. Sí, sí, por mí va bien, que entre una y otra. It's not the presentation. This is it's not your presentation.
Is it not?
No,
No, this one, no.
So, yeah.
But it's what you have there, yes.
Yes.
That's a weird version of this is not here.
Yeah, that's good. Yeah.
We are watching one.
Oh, yeah, we're watching another one. And I don't understand sincerely why.
Laser coming on the computer. You press L, digital laser on the screen.
Yes?
Yeah.
But he is
Yeah, I feel
he
more comfortable.
is the beast.
That doesn't matter. I don't need.
Okay.
¿Te funciona el láser ahí? No, ¿verdad?
¿Qué?
¿Funciona ahí?
No, pero si le das, te quitas ahí.
O sea, vas a utilizar el bit. Ah, no vas a utilizar el láser.
No, no. Okay. Good. Okay. Well, good morning, everybody. Thank you, Noelia, for the introduction. In my talk, I'm going to present some results obtained for a minor study of energy decomposition analysis and topological analysis of the electron density to understand the large stability of rare case complexes in the lowest line cycle state. These complexes are known as excimers. So my presentation is much more fundamental than the previous one, but this is, I think it's an interesting topic too, for spectroscopical interest, maybe. Well, this is the outline of my presentation. I will first introduce briefly the theoretical framework of our energy decomposition analysis, the DDI from now on, for the study of ground state complexes, focusing on the definition of intermolecular exchange and spin repulsion, which is necessary to calculate the Pauli repulsion energy at post-SDF level, because this allows us to extend our analysis in ground state complexes to cycle state complexes. Okay, and finally, I will present the results obtained for the neon, argon, and krypton diodes in the cycle state. Well, the main idea behind the DDI scheme is twofold. On one hand, we can express the interaction energy, which is defined as the difference between the complex energy and the sum of the energies of the molecules, molecular fragments, or atoms. In this case, we can express it as a function of the one electron density or the one electron density matrix in terms when we deal with kinetic energy terms. Also, as a function of the exchange correlation density and the nuclear potential, which in the case of a complex is just the sum of the nuclear potential of the fragments. On the other hand, we can decompose the one electron density of a complex as a sum of the one electron densities of the isolated fragments plus the deformation densities associated with the spin repulsion, which arises from the Pauli exclusion principle, and the polarization, electropolarization, which is due to the interaction between electrons and nuclei from different fragments. We can do the same for the exchange correlation density, but in this case, the term associated with the Pauli principle is called the intermolecular exchange density. Well, introducing this the composition of electron densities into the expression of the complex energy in the equation of the interaction energy, we can identify and remove the terms that are exclusively due to the energies of the isolated fragments, leaving only terms that are related to the intermolecular interactions. These terms can be grouped in energy components that has the same physical origin, like for example the electrostatic energy, the exchange intermolecular exchange energy, the spin repulsion energy, and the polarization energy. Further, we can decompose the polarization energy into induction plus dispersion using a perturbation scheme, second order perturbation scheme. On the other hand, the exchange and the repulsion, spin repulsion energies are the well-known Pauli repulsion energies, so mentioned both. Well, the Pauli energy is the most intricate point of our scheme, especially for calculation at post-SDF level. We will start with explaining how to calculate it at SDF level. the spin repulsion density and the intermolecular exchange densities are the density we have to define to calculate the power energy. Okay, so at SCF level, where the spin repulsion density is defined as the difference between the one electron density obtained from an anti-symmetrized wave function, the product wave function of the isolated fragments of the wave functions, anti-symmetrized, this one, which satisfies the Pauli principle, and the electron density obtained from the Hartree product, this one, which doesn't satisfy the Pauli principle. Okay, in the case of the Hartree product, we can see here that the one electron density is just the summation of the one electron density of the isolated fragments. And in the case of the anti-symmetrized wave function that satisfies the Pauli principle, okay, the one electron density can be obtained from an orbital set, which is obtained by orthogonalization of the occupied orbitals of the isolated fragments. Well, in the case of the intermolecular exchange density, the exchange density at SCF level is easily obtained from the occupied molecular orbitals. So the intermolecular part of the exchange density is just the difference between the exchange density obtained from the orthogonalized orbital set, so wave function that satisfies the Pauli principle, minus the sum of the exchange densities obtained from the occupied molecular orbitals of the isolated fragments. Wave function which is not anti-symmetrized. Well, this is the expression of the intermolecular exchange density in terms of density matrix elements, okay, and basis functions. This is the expression that is implemented in our scheme. Well, let's move to post-SCF level, the intricate point. At post-SCF level, a spin repulsion density can be obtained in a similar way as SCF. But in this case, instead of the occupied molecular orbitals, we have what we call, in quantum chemistry, the natural orbitals and the occupation numbers. Okay, so the difference here is basically that in the orthogonal, to obtain the orthogonalized set of orbitals, we have to orthogonalize natural orbitals. And the natural orbitals have different weight, a weight that is given by its corresponding occupation number. So here we perform an a weighted orthogonalization instead of the typical loading orthogonalization procedure, which is a little bit more complicated. Well, but the most complicated point is to obtain the intermolecular exchange density, because the one electron density in the case of post-SCF methods is not even potent. So we have to deal with the two electron density metrics, which for the case of medium and large systems is a very complicated task. So here in our scheme, we introduce the one electron density approximation of Mueller, where the exchange density is obtained in a similar way at SCF, but instead of occupied orbitals, the natural orbitals, and multiplied by the square root of the occupation numbers to satisfy the necessary representability condition of exchange density. So the intermolecular part is then obtained in a similar way as in the SCF. The difference between the exchange density obtained from the orthogonalized set of natural orbitals minus the summation of the exchange densities obtained from the natural orbitals of the molecular fragment. Always multiplying by the weight factors, which are the occupation factors. And this is the expression in terms of density matrix elements and basis functions. It is similar to the SCF case, but in this case, we multiply by the square root of the occupation number. So that means that at SCF level and post-SCF levels, using this one electron approximation, the computational cost in terms of computational time is quite close between both levels for the step of the energy decomposition analysis. This is a very important result. Okay, let's demonstrate that the one electron approximation we introduced to obtain the Pauli energy is not relevant. Okay, for the results obtained. So it doesn't comes with large errors. Here we can see in this table a comparison between the electrostatic on one hand and the Pauli energy, which is the sum of the intermolecular exchange and spin repulsion energies between our scheme, the DDI, and the symmetry adapted perturbation theory. Okay, this is the most popular method to analyze, to decompose intermolecular interaction energies. Okay, for 8 different diagrams. Here we can see, remarked in yellow, the differences that we can observe at SCF level. So Hartree-Fock, SCF, and CCSD is post SCF level. Okay, SCF is Hartree-Fock is the simplest level. We can see that the differences are small and negligible in the case of electrostatic energy. Okay, at post SCF level, the differences between SAP and the DDI results are larger, but they are still very small, which values the differences that never overpass the 4% in the case of electrostatic energy and the 10% in the case of the Pauli energy. Okay, this is an expected result because the post-SDF wave functions are multi-determinant wave functions, okay, where the optimization of the wave function is more affected by cutoff and threshold introducing during the optimization. So this is the expected result. But these larger differences could be also affected by the one electron approximation. This is what I want to demonstrate that is not a relevant factor. But what we can observe also is that at SCF level, also the differences between electrostatic and Pauli energies are large. Okay, so we are confident that our one electron approximation is not relevant, and that this increase in the differences at post-SCF level is due to other factors. Well, let's move to the analysis of recycled state complexes. Okay, here in this slide, I'm showing the most popular methods employed to obtain the electronic structure of recycled states, including single reference and multi-reference wave function methods, and within single reference, those employing a single determinant wave function or a multi-determinant wave function. In yellow, I am indicating those methods that are currently implemented in our scheme. Within these 3 methods, we include the 2 most employed single reference methods to investigate excited states: time-dependent DFT and equation of motion coupled clusters single sample. Okay. But the question that we can, with this one electron approximation, we can investigate ground state complexes at post-SCF level, and that from the excited state methods, we obtain a one electron density that metrics that can be diagonalized to obtain natural orbitals and occupation numbers. That means that we can extend our theoretical framework introduced before to the study of excited states. Such states we use natural orbitals and occupation numbers too. So, but the most intricate point here is the definition of an appropriate and a proper electron density reference for the electron density. So we have 2 limit situations: excitonic molecular localization, where the electronic excitation in the complex is perfectly localized in one of the molecular fragments, molecules. Okay, in this case, the reference density, I mean the reference density is the density for the non-interactive systems, okay, is just the summation of the electron density for one of the fragments in one state and the other in the cyclic state. The other limit situation is excitonic molecular delocalization. In this case, the electronic excitation is perfectly delocalized along 2 symmetrically equivalent molecular fragments. For example, the systems we are going to study, the X-mer complexes. Okay, in this case, the best choice for the reference density is an average of the excited state and ground state densities of both molecular fragments or use. Okay, let's move to see the results obtained for the neon, argon, and krypton dimers in the first lowest lying excited state. Well, the first step was to evaluate the effect of the basis set incompleteness error and the basis set superposition error in the calculation of the total interaction energies. As we can observe here, we did it by performing calculations with a augmented correlation consistent basis set of increasing size. As we can observe here, the calculations obtained with the counterpoise correction for the basis set superposition error lead to large errors. We obtain even positive interaction energies, so repulsive complexes. The calculations without counterpoise correction, we observed that we have a compensation of the basis set incompleteness and the basis set superposition errors. Perfect compensation in the case of time-dependent DFT, but not in the case of equation of motion coupled clusters. These are the results of the without counterpoise. However, we performed a further analysis and we used a doubly augmented triple set correlation consistent triple set basis set. And we observed that in this case, the results are free of basis set incompleteness and free of basis set superposition error. So we selected this basis set for perform the energy decomposition analysis. Well, this is a summary of the results obtained for the energy decomposition analysis. Okay, we did it at the independent DFT level with the M062X D3 functional and the basis set I mentioned it before, and also using the equation of motion CCSD. We didn't perform the splitting of the polarization. 4-420, no. Oh, you didn't split the polarization unit induction and dispersion because the double augmented basis set has a lot of diffuse functions, so these diffuse functions does not guarantee the proper definition of the atomic domains, which is necessary to calculate the induction energy. So we just analyze polarization as just one energy. Well, another thing, we have compared the results obtained for the excited state with the results obtained from a ground state complex in the same geometry of the excited state. So upon a vertical electronic relaxation. So this is to understand better why these complexes in the excited state are so stable. So we have found that the electrostatic energy is double value in the excited state and in the ground state, so contributing to the stabilization upon electronic excitation. On the contrary, we have observed that the intermolecular exchange density we expect that increase in the case of in the excited state with respect to the ground state. It contributes marginally to the stabilization of the excimers because the values are quite similar in the ground state. On the other hand, the spin repulsion energy is large, as expected, because of the proximity of the atoms in this excited state geometry, but it also increases by a factor of 1.5 upon the electronic excitation. So this is stabilizing the complex in the excited state. But it's definitely the polarization energy which explains the large stability in the excited state. As we can observe, upon electronic excitation, the polarization energy increases dramatically. Okay, this energy is comparably pronounced very large in the three excimers. The values are more or less the same, but the enhancement factors shown here on the left are quite different. Between neon and argon and krypton complexes because we observe the differences in the ground state. Well, okay, so The polarization, the energy composition analysis provides quantitative information about the role played by each intermolecular force in the stability of the complex, but we can obtain extra information, qualitative information from the deformation density plots. Here we can see the polarization density for the excited state and the ground state. As we can observe, the polarization density increases dramatically upon the electronic excitation in agreement with the values of the energies. What we observe here also, it's an electron density accumulation in the intermolecular region, surrounded by electron density deflection. The accumulation is represented in magenta color, which is associated with dispersion interactions. Okay, we can observe also that the accumulation is obtained only at the equation of motion coupled cluster single double level, not at time-dependent DFT, reflecting the problems of DFT models to characterize dispersion effects. But the most interesting here is the intramolecular reorganization of the electron density from sigma to pi alignment here, which is characteristic of what we call in the theory of the Excimer theory, excitonic coupling. Okay, this is comparably pronounced in the three Excimers too, and the effect is much larger, significantly larger than the dispersion effect, indicating the important rule, the key role that the excitonic coupling plays in the stabilization of the rare case Excimers. So this is my last slide, sorry. Of course, the excitonic coupling should be related with an increase in the covalent character after electronic excitation. Previous works suggested this question, but not quantified it. We have calculated the domain average Fermi-Hall density plots and the covalent bond orders using quantum theories of atoms in molecules, and we can see in this DAF and DAF different plots upon electronic excitations that there is an increase of electron delocalization between atoms in the excited state, corroborated quantitatively, but bond orders that are in all cases larger than 0.5 and close to 1, which is the ideal value for a single covalent bond. The Excimer complexes are largely covalent. And this is funding, help with the Ministerio, Junta de Galicia, Universidad de Vigo, and of course, thank you for your attention.
So, some very briefly curiosity. There is one want to ask something.
I have a question, but maybe it's too long.
Too long.
Yeah, I'm right. It's about the density of the spin density of the dimer. You say, if I remember right, I'm correct with this, if that's true, if I'm wrong, that in order to calculate it, you took the density of the monomers and you orthogonalize them, right?
The orbitals. I orthogonalize the orbitals because what I need is a wave function which is anti-symmetric.
Yes, yes.
The problem is the orbitals of this fragment and the orbitals of the fragment are not mutually orthogonal.
Yeah, that I know.
Okay.
My question is not this. What is the difference with getting directly the spin density of the Pauli density, we have to call it like that, of the dimer, the direct dimer?
For the Pauli density, we have to avoid the electrostatic interactions. So you want to see only the effect on the dimer. It's like you divide the process in steps. The first step is anti-symmetrize the wave function. Why? Because the Pauli effect, the Pauli exclusion principle changes density. Okay, but you want to avoid the interactions between electrons and nuclei. So it's like your density is frozen, okay, and the change you obtain is just because of the Pauli exclusion principle. So I have a wave function in the isolated fragment that is not antisymmetric, and now I anti-symmetrize the wave function. I can use these orbitals and these orbitals here of the isolated fragments, but the problem is they are not orthogonal, so the computational it's a challenge computationally to do with that, because you have a lot of overlap integrals there.
Yeah.
So I orthogonalize these orbitals, and then it's much more simple.
Okay.
Construct the wave function with this orbital, and we'll take this.
Yeah. Yes.
Okay.
Sorry.
So the next speaker is Jose Manuel Hermida Ramon, and he will speak about molecular dynamic simulations of nanoemulsions, effect of the initial geometry and concentration. Y encima las preguntas.
Okay. Okay. So, good morning, everybody. I'm going to talk today about computational strategies in the study of food and nanoemulsions. This is a work that we have been doing in collaboration with some experimental group of our university, the University of Vigo. Today, I'm going to talk a little bit about two main nanoemulsions, that is the gallic acid and the tocopherol, and also in the middle, I'm going to talk a little bit about the tocopherol cyclohexane complex. So, lipid oxidation is one of the main causes of food degradation, food quality degradation in oil and water nanoemulsions. The key point of this problem is that the lipid oxidation depends mostly on the concentration of the antioxidants in the interface and not in the bulk, and not the stoichiometric concentration. So, and the question is that from an experimental point of view, they could more or less calculate how much antioxidant is in the interface, but they don't know, they can get any molecular information about that. They cannot, for instance, know about the orientation of this antioxidant, which is important in order to see if they are effective or not. So, because of that, they asked us, to the computational chemistries, how to provide them with information about that. In order to do that, what we did in our group, it was to combine different methodologies. We used DFT calculations with classical molecular dynamic calculations, and also QMM simulations. So, yeah. Doesn't work now? Yeah.
It's not working.
No.
The pointer.
No, but maybe with the computer. Okay, let's see now. Yes, so it looks like now. Yes. So the first system that I'm going to talk about today is the gallic acid nanoemulsion. In here, we took this number of molecules that you can see here, that they correspond to the experimental ratios, and we simulate that one. We simulate, this is more or less the system that we simulate. And in order to simulate it first, we use classical molecular dynamics. We use the global Lambert force field. This is a force field that originally was created for proteins, and we just started with that one, but we saw that the results were quite okay, so we just stuck with that one. Then, then we performed the simulation. The protocol that we use was this one. This protocol is for this system, but also for the other ones that I'm going to flip today. We start with a initialization, then a heating, a calibration, and then finally a production, where we got from that one several conformations. In this case, was 100,000 conformations that we used to analyze. Then, from the analysis, we got some density profiles, and from that one, we could calculate the distribution of the antioxidant. In our case, for instance, we got that the antioxidant, it was 100% of the antioxidant was in the interface, which is a good result because experimentally they got 81%. So we are very close to experimental results. But that's something that the experimental already have. What they didn't have, it was the orientation. We could provide them with the orientation, and that is something like that, which is acid part oriented to the aqueous phase. That is, in fact, the part that is involved in the antioxidation procedure. Sorry. Now, once we got the information from the classical molecular dynamics, we wanted to know a little bit more about the chemistry of the oxidation behind that, the chemistry behind the oxidation. In order to do that, we perform DFT calculations, and also we calculate using a QMM setup, where we calculate the system, where the core it was the antioxidant and also the radical that creates the oxidation, and a UMM region where we just simulate the environment. From the DFT results, we got the barriers of the propagation reaction. That means the reaction between the radical and the oleic acid that create the emulsion. So each time that they react, the emulsion is getting degraded, so is getting worse. And the inhibition, that is the reaction between the radical and the antioxidant. Once this one occurs, the oxidation of the system stops. So we saw that the barrier with the antioxidant, it was almost twice smaller than the barrier with the propagation reaction. Because of that, we could prove that the gallic acid is a good antioxidant. Then, we perform QM calculations where we submit 4 different trajectories. Here is supposed to be a video where you will see that in 2 of these trajectories, there is a migration of this hydrogen to the radical. So it stops the function of the radical, so it stops the oxidation. With that, we prove also that this barrier of 7 kcal get lower in experimental conditions, so the antioxidant perform his function as stopping the oxidation reaction. Then the other system that we studied was the cyclodextrin tocopherol complex. The tocopherol is another antioxidant. Experimentalists usually use the cyclodextrin in order to deliver the tocopherol to the interface. So what the experimentalists wanted to know is which configuration, how the tocopherol was inside the ring of the cyclodextrin, if it was with a hydrophilic head inside the ring or with a hydrophilic head outside the ring. And also another thing that they wanted to know, it was the free energy of this complex in water, because they couldn't calculate it in water. They could calculate it in a mixture of different solvents, but not in pure water. So in order to provide some information, we performed first a conformational search, where we started with classical molecular dynamics in order to get some starting geometries. And from this 30 geometries, from this 30 geometry, we performed DFT calculations. We got 9 geometries, 9 minima, where we perform infrared spectrum, which simulate the infrared spectrum, and also from the 2 global minima for each global minima of each configuration, we simulate the NMR spectrum. In order to also provide with the free energy, we perform a DFT and a QM setup where using first a molecular semi-empirical calculation, a molecular dynamics semi-empirical calculation. We got 1,000 geometries, And then we calculate the building energy and the free energy for all of them in order to provide using continuum, a continuum model to describe the water in order to provide and to obtain the free energy in water. So our gas phase calculations told us that we have two complex, one with a head inside the ring and another one with a head outside the ring. And in gas phase, the complex one, the one with the head inside the ring, it was 2.6 kcal more stable than complex 2. When we then compare the infrared spectra and the NMR spectra with the experimental results, what we got is that in the experimental conditions is complex 2, not complex 1, the one that occurs. So in gas phase is complex 1, but in liquid phase is complex 2. So also the free energy that we calculate for using DFT methodologies for this complex in water was 8.3 kcal. Then we also, in order to obtain more information, we perform classical molecular dynamics calculations with this system as here. We got 75,000 geometries that we analyzed, and also we perform stereo molecular dynamic simulations in order to obtain the free energy. Yeah. Okay. The analysis of the 75,000 configurations show us that complex 2 is the most commonly that is the complex that most likely appears. It was 75% of the time. Complex 1 was 25, and then there is something in between that is 1%. Sorry, 8%. Then our still molecular dynamics calculation, we perform 80 as we use, and then using the Zagatinsky expression, we got the free energy. What we got it was that the free energy was minus 9 kcal/mol, that is close to the DFT results, and it's almost twice the experimental result. But the experimental result is in ethanol water, not in pure water. And in ethanol, the tocopherol is more stable than in water. So we can expect a smaller, or you want to call it less bigger free energy complexation in this experimental mixture. So yes, that in pure water. Finally, the last once we got the tocopherol cyclodextrin complex, we move on to the tocopherol nanoemulsion. In that one, this is a picture of our initial starting point. What we studied here was how the concentration and the starting points of the simulation, how the starting point of the molecules affect the behavior of the antioxidants. So in order to do that, we perform 4 different simulations, changing the number of tocopherol and cyclodextrin molecules, and also another one where tocopherol it was inside the oil core, and the cyclodextrin it was in the surface, and another one where the tocopherol and the cyclodextrin were both on the surface. We perform the molecular dynamic simulation, 1 microsecond productions, and we got from that one, we extract 250,000 snapshots. Okay, what we saw here is that the concentration and initial point change the thickness of the interface. So it depends on that one, the size of the interface depends on both. Also, we saw that tocopherol, that is the antioxidant, goes towards the interior of the oil droplet. But the important part, that is the hydrophilic head, that is the one that has the antioxidant function, points toward the aqueous phase, which is what they want, because the radical came from there, or is in there, and is the one that we wanted to stop. well, from this is very qualitative, but from the interaction between tocopherol and cyclodextrin from this from the point of view of force, they are dominated by dispersive force, and in this nanoemulsion, there are not much hydrogen bond between tocopherol and cyclodextrin. As a future work, well, some of them are already been done, and we are still analyzing the results here now, is just perform this kind of simulations, but with the tocopherol cyclodextrin complex altogether, not one for each part. Also, obtain the free energy of the core of the escape trajectory of one tocopherol molecule, and also of the complex from the droplet, so going from inside to outside. And finally, obtain also QMN simulations of the reaction of tocopherol with the peroxide radicals. And with that, I'm finished for today, and thank you very much for joining.
Thank you. Some questions, curiosity. I have curiosity. How many atoms is the gamma tocopherol,
Okay.
the system?
Okay. This green line is the tocopherol.
Yeah, how many atoms? More or less.
I will say it's 12. I will say something like 30, maybe.
So when you will do the QMM, how decide which is the part of the system that will be running with QMM?
Okay, what we did, in fact, it was rather easy. It was due to the computational cost. We took a tocopherol. Well, in fact, that one was already done with tocopherol. It was with the other one, but doesn't matter. We will take a tocopherol. Then we take the radical, that is a oleic acid radical, okay. We put that one. And what we did, it will be the same. We look for conformation to where they are close.
Okay.
And these two molecules are going to be treated as QM. Then you treat, let's say, a radius of, in the gallium nitride was at the 12 angstroms. With MM. Free with the molecules that can freely move, and then from 12 to 20 with the molecules that they cannot move, and then you perform the QM.
The QM.
What I wanted to plan it to do is instead of using only 2 molecules of QM, use 3. The radical, 1 oily molecule, and then the antioxidant.
But it's a lot of atoms, or not?
No. I mean, it's a lot of atoms. Yes. But with the new computer,
okay.
I think we can do it.
Okay.
The question, I mean, each QM calculation with ORCA, each QM step took something like 30 seconds. So more than that.
No. Okay.
I think with the new computer, we can get the oleic acid, the peroxide radical, and the
okay. Okay. Thank you. Some more questions.
How this is right?
This one.
Conformation acid. Maybe I didn't understand.
I can explain very quickly. So yes.
Classical molecular dynamic simulations in that phase, 30 geometries. What do you mean? You got 30 geometries from the 30 geometries from the molecular dynamic simulation.
Yes.
Okay. To perform
optimizations with the
optimizations. But then, for example, optimization at B3 lead, 9 geometries.
That was wrong from this set.
To get an average spec. To get an average spec.
No. The spectral, it was obtained from the minima. Yes. But not averages.
Then these are not anymore thermally averaging. No, because you perform an optimization, PFT. You perform it at quantum level. So.
Yeah. But remember, this was done for gas phase.
Yeah.
Not for,
okay.
It was for gas phase. No, we didn't want it to describe the liquid phase with these calculations. It was just for gas phase. That was in order to get the minima. It was a conformational search to get all the possible media.
Yeah, okay. I understood.
Okay.
Thank you again. See you with the chair of this session in the afternoon. I'm sorry for the late.
Because of it.
Sì, sì, sì.